Yes, I hope you can hear me.
Yes, and we can see you.
Yes, perfect. First of all, good evening, everybody. I'm glad and honored to be here and present our work. I'm representing the team from West University of Timișoara, and I'm going to present our paper called Predicting Car Use with Big Data. I'm going to go through these steps. Namely, I'm going to talk about the research motivation, the limitations of current research, the present study, and I'm going to go through methodology, results, limitations, and our conclusions. I think my presentation ties in quite well with what my colleague presented before with the, with the availability of parking spaces and reducing congestion and pollution in cities, because this is one of the most important motivations of the present study, namely that road transportation is one of the main responsibles for the CO2 emitted into the atmosphere, and it contributes significantly to global warming. Besides this, it also is responsible for about 11% of all particulate matter emitted into the atmosphere. So it contributes significantly to urban pollution. And in the European, as I said before, is responsible for about 22% of all the greenhouse gas emissions. What is more shocking is that while other sectors like industry, agriculture, and so on are decreasing their contribution to global warming, the contribution of the transportation sector is continually rising, and it will do so in the following decades as parts of the world like Asia, Africa are developing and becoming more car dependent. Probably this is gonna rise as well. Uh, Besides this problem, urban road transportation is also responsible for congestion, pollution, as I said before, noise, the large majority of accidents, and loss of urban space. These are, of course, only negative aspects. Nobody is denying the positive personal and societal benefits that cars have for us. But of course, these benefits come also with a huge drawback when we're talking about excessive car use. Uh, the field is quite new. The field of understanding the motivations of people to drive cars is quite new. And one of the main limitations is that we don't actually know which are the most important predictors, the most important causes of people choosing to drive instead of using sustainable means of transportation. And this is because scientists have studied car use from four different complementary perspectives, namely psychological, engineers have studied more structural, and also people in the legal system have also studied this structural aspect of how you can devise legislation and incentives to move people away from cars. Others have studied the demographic aspects, and other scientists have concentrated on the contextual aspects that influence people to drive or not. But unfortunately, most scientists have focused solely on a single perspective, and these predictors are not reunited in more comprehensive models. This is a problem because generally when you put more predictors into the same model, you generally see a decrease in the effect of those predictors. Some might even become non-significant. So that's why I'm saying we don't really know which are the predictors and how big are their effects. Another drawback is the weak methodological design of studies in the field, as most are correlational, and studies that evaluate intervention effectiveness to reduce people's car use are generally pre-test, post-test evaluations without a control group, unfortunately. And probably the biggest limitation of the field is that it's almost exclusively based on self-reported measures. I personally know just 3 studies that use objective measures. People are generally asked how often they drive or what is their number of kilometers that they drive during a week, or in the best case scenario, they are asked to keep a journal of their travels, the means of transportation, and the kilometers that they traveled with each mean. But as I said, objective measurements are quite rare. Our study, predicting car use with big data, addresses some of these limitations, and most importantly, it measures car use objectively through GPS measurements. It also uses a wide array of predictors, namely psychological, structural, contextual, and demographic predictors, and I'm going to go through them very briefly a bit later, and also uses some more modern statistical techniques, namely multi-level modeling. Regarding the methodology, we had a sample of 48 individuals, all from Timișoara, with ages between 18 and 53 years, mean 29, among which 44% were female, and they all completed a questionnaire with the self-reported data, like psychological measurements, and uploaded their mobility data in a Dropbox account by using a code for both, which we could connect the both pieces of data. Their mobility data consisted on Google location data, which they had to download and upload in the Dropbox account. We used a longitudinal design for 7 days, in which we followed their transportation patterns for a whole week. This is how the data was structured. Basically, there were 2 levels of variability. The day-to-day variability for each individual, and so this is the intra-individual variability, because we assumed that there is variation from day 1 to day 2 to day 3 and so on for each individual. Not everybody drives the same number of kilometers every day, for example. And the second level of variability is between persons. So individual A might drive more than individual B, and so on. And for each level, we had different predictors. So we had a multi-level model with 2 levels. And at level 1, we had the inter-individual predictors, namely wind speed, and plus means that we expected a positive correlation with the DV, which was number of kilometers traveled. So the bigger the wind speed, the more people traveled by car. The bigger level of precipitation, the more they traveled by car, and so on. Distance, whether they needed to do shopping, whether they needed to take the kids to or from school, the temperature and day of the week. We didn't have a hypothesis, but we treated this as an exploratory analysis. We coded these variables, some of these variables, by following the GPS points on the map. For example, whether they were stationary in a supermarket, we coded that they were shopping. Whether they were stationary for a certain period, which we used in a coding scheme, next to a kindergarten or school, we coded that they were taking their kids or taking the kids to or from the school or kindergarten. At level 2, we had other predictors, namely the variables from the theory of planned behavior, which we expected to predict negatively the number of kilometers traveled. And here we had attitude toward car use reduction, subjective norms for car use reduction, and perceived behavioral control to reduce car use. We also had the variables from the norm activation model, namely awareness of consequences of car use, description of responsibility for those consequences, and personal norms to reduce car use. We expect it to correlate negatively with kilometers traveled. Intention to reduce car use, access to alternative transport infrastructure like cycling paths or public transport, car use habits, and some exploratory analysis proximity to PT station, public transport station, age and gender. This is how the model looks. Basically, we built three models. The first model is an intercept-only model in which we separated the variability on level 1 and level 2 to see whether there is a significant variability at level 2 and if a two-level model is required, and it is. In model 2, we added in a saturated model all the predictors from level 1, and we removed one by one all the non-significant predictors, starting with the predictor that had the highest p-value. And we ended up with these three predictors that were significant, namely distance that they needed to travel, whether they needed to take their children to school, and whether they needed to do shopping. And in model 3, we added all the level 2 predictors, and it's the same in the saturated model, and extracted those non-significant predictors, staying with habits, the car use habits, and access to alternative transport infrastructure. The M3 predicted 58% of the variability at level 1 and 87% of the variability at level 2. All in all, about 70% of the variability was displayed by the model. If we look at the beta effect, by far the largest effect is of distance. So the more people need to travel away from home, the more they use their car. And the other ones had small effects, generally betas of 0.1. Of course, there are limitations. First of all, we used low and non-representative samples for Romania. There were some variables which were coded by a single person, for example, the number of kilometers traveled, shopping, and kids. But we are trying to address this limitation by using the code to extract data instead of coding manually these variables. We also use the restrictive statistical model in which all the predictors predict the DV, so they are all at the same level. A more realistic model would be a multi-level SAM in which predictors are at different levels of predictability, and we can also study mediation processes between the variables. And I didn't put here, but another limitation is the time period of 7 days that we measured car use. You can imagine that is not a lot of variability in weather, for example, at least in what's concerning the temperature. So following the transportation patterns for a longer period of time, we can see how the weather aspect influences car use. As conclusion, all types of predictors, psychological, structural, and contextual variables significantly predict kilometers traveled. Contextual factors like distance have the largest effect. Unfortunately, there is limited space for psychological interventions, which are generally the preferred one. And probably the most important conclusion is to reduce car use in cities with mass focus on better city planning, with daily necessities in close proximity. So cities have to be designed at residential areas, and fun and cultural and social and so on, educational facilities, sports facilities are in close proximity of each other. Thank you very much. If there are questions.
Thank you. How do you get the data? So you have in your article some images where it show the location. How did you get that data?
It was quite difficult because it's sensitive data. But we use some motivation. For example, we gave them Amazon vouchers, and we the biggest prize was a
No,
bicycle.
no, no,
Uh,
technically. So you have
Technically,
technically, yes.
what do you mean by
So
by
you
this?
have 1 second. So you have
How did
here an example of a route in which the car was used. How do you get that data to put in that example?
Okay. So they had to download their Google location data. They had to go into their account, Google account, download the data, send it to us via a code. So it was all anonymous. Then we loaded that data in a program that is called Location History Visualizer. And with the help of that program, we coded the number of kilometers and the other variables.
Okay, maybe in the future it will be good to develop an application that gets the data and sends to a server, and you automate this process.
Yeah, would be very interesting because there is no such thing on the internet. Right now, we are writing an R code that basically does that to process the data and extract the variables that we are interested based on the codes that based on the rules that we use to code. So yeah, we are at the first step of that.
Okay, thank you.
Thank you very much.
So I think that